Okay, so what we'll do is we'll want to substitute Darcy's law into our conservation of mass equation. But just to make things simple at first, I'm just going to use the Darcy flux for a few manipulations. Okay. So I'm going to substitute in. I'm going to substitute in the fact that V is equal to Q over phi into our conservation of mass equation, so that then we have okay, and the next thing I'm going to do is everywhere I can, I'm going to use the product rule. Okay, so I'm going to use the product rule in the first term, so that leaves that guy. Now, should be understood that the density is actually a function of pressure and space. Likewise, the porosity is a function of pressure and space. And so with this knowledge, everywhere that I have a density or everywhere that I have a porosity, I'm then going to use the chain rule in such a way that, well, you'll see it as it comes out, but I'm going to use the chain rule in such a way that I end up with gradients of pressure. Okay, so spatial and temporal gradients of pressure. Okay, so the first thing I'm going to do on this first term here is I'm going to factor out the rho phi. So if I factor out a phi rho here, then what I'm left with is 1 over phi there times, and then I'm going to use the chain rule. I guess I'm reversing. I'm working on phi first, but it doesn't really matter on the phi phi dt. But so I have 1 over phi partial rho partial p partial p partial t. It's just via the chain rule, plus 1 over rho partial rho partial p dp dt. This is phi here, sorry. All right. Well, if you remember from your petrophysics class, this is known as the compressibility of the rock, and this is the compressibility of the fluid. Okay. So now turning our attention to this term, we'll do the same thing in terms of using the chain rule with the knowledge that the density is a function of pressure. Then we have partial rho partial p grad p q plus, and then on the last term there's no manipulation to be done at this time, so we just have rho divergence q. That's all equal to 0. So now I'm just going to divide the whole equation by phi, right, and write it all out. So we have now phi compressibility of the rock plus the compressibility of the fluid, dp dt, plus 1 over rho and we can see here again we have the compressibility of the fluid, and we're also going to define the compressibility of the rock plus the compressibility of the fluid as the total compressibility. And so in the next step, we're going to go ahead and substitute in Darcy's law in for this Q vector, the Darcy flux. So again, we have that Q is equal to K minus K over mu grad P. And of course, you also have the rho G term, but in what follows, we'll just, for simplicity, we're going to assume that any flow is horizontal, and so therefore it has no effect. The gravity has no effect. So essentially, it's a 1 or 2-dimensional reservoir in the horizontal plane, and so we're going to ignore the effects of gravity. And this is just to make the equations a little more concise in what follows. And so if we substitute that back in, to our final result, our final line here, then we have phi ct dp dt now minus, we'll also make the assumption that, okay, so let me write down the assumptions. We're going to make the assumption that the permeability and the viscosity are homogeneous and isotropic. So homogeneous, isotropic, no gravity. So those are the assumptions here. And so if with homogeneous and isotropic permeability, then I can move them outside. Well, I guess I'll write it out as it is now, and then we'll put those assumptions in one moment. Okay, so what I was saying is because we're homogeneous and isotropic, then there's no spatial variation in these functions in K and mu, and I can move them outside this divergence operator. And so with that, then I can factor out and sort of rearrange this equation in a way that I have phi ct now mu K dp dt is equal to the divergence of the pressure gradient plus the compressibility times the dot product of the pressure gradient. And so this is the general form of the diffusivity equation under the assumptions that we made. Because in general, the compressibility is a weak function of the pressure. If we assume that the compressibility, so we're going to say if we assume small and constant compressibility, small and constant compressibility, then you have something that's small and constant multiplying a nonlinear term in pressure, and so then therefore we can ignore that guy. And with that, then we'll have our final form of the diffusivity equation, which is often written like this. And this guy is known in mathematical circles as the heat equation. or in our context, it's the pressure diffusivity equation. And of course, alpha is equal to, alpha is just this constant over here, mu phi ct over k. Now the reason we made all those assumptions to get there is because this is an equation that can actually be solved in closed form analytically. So this is one of the, well, at least in one dimension. In one dimension, it can be solved closed form analytically. So let's look at an example.